Welcome to the Space Telescope Public Lecture Series. Tonight's talk, Active Galaxies, Monsters of the Deep, Space. Travis Fischer from the Space Telescope Science Institute will be presenting. I am your host, Dr. Frank Summers of the Office of Public Outreach here at the Space Telescope Science Institute. I note that our public lecture series will continue to be online only throughout 2023. And of course, I always want to thank our amazing tech team, which is usually Thomas Marufu and Grant Justice. However, playing the part of Thomas Marufu tonight is Kevin Flynn. Thank you, Kevin, for filling in kind of last minute, because it was only this afternoon that we had to change up our personnel. Our upcoming talks in April, Exploring Rocky Worlds on the Precipice of a New Frontier by Catherine Bennett, also of Space Telescope Science Institute. In May, Amanda Pagul will be presenting a talk that doesn't have an exact title yet, but it will be on galaxy clusters and the frontier fields. So these are galaxies out at the edge of the universe. And on June, our June talk will be done in association with a science conference on the Nancy Grace Roman Space Telescope. So they have asked us if we can delay it and actually put it on a Thursday. Yes, not a Tuesday night, a Thursday, June 22nd. So note that special date. About the Nancy Grace Roman Space Telescope, but they haven't told me who their speaker is going to be. So that will be a special event, and I will give you the details of that next month. Or you can find them on our website, www.stsci.edu/public-lectures, where you will find this webpage. On the left, you can see the link to our webcasts, both our YouTube playlist and our webcasting on the STSCI webcasting page. And on the right, you can see how easy it is to sign up for our monthly emails. Just enter your email address, hit that subscribe button, and you'll get like 2, maybe 3 emails per month. Also on our website are our list of upcoming lectures. And if you click on any one of those lectures, you will get the full details, including its description and links to the STSCI webcast after it's been recorded, and also links to YouTube. Our email, we send it out just as I said, a couple times a month. I showed you how to sign up the website. You can also, to get notifications, subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word, Hubble Space Telescope. You'll get notices of new videos as well as reminders of live events like this. Finally, if you have comments or questions, you can send them to publiclecture@stsci.edu. We handle social media here for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute. And you'll find them on Facebook, Twitter, YouTube, and Instagram at the addresses listed. I don't do much social media, so if you want to follow me, you're going to be kind of bored, but you will find a few interesting things every now and then on Facebook and Twitter at Dr. Frank Summers. And now our news from the universe for March 2023. Our first story for you, the bespoke rings of Saturn. Well, Hubble has taken a lot of images of Saturn. And in the late 1990s, we got images of Saturn every single year. And you can see in the upper left, starting in December 1994, and then 95, 96, 97, 98, 99, and 2000. And you can see how the orientation of Saturn relative to Earth changes as Saturn moves around its orbit, because it's not flat. That ring plane isn't flat to the ecliptic. It's actually tilted. So as Saturn moves around the solar system, the ring plane looked at different various tilts. And Saturn actually takes about 30 years to complete an orbit. So Each season on Saturn lasts for about 7 years. That'll be important in just a second. We continue to take pictures of images. Matter of fact, we have the Outer Planets Legacy program called Opal, and Opal got this beautiful image of Saturn in September of 2022. Yeah, just another gorgeous image. Saturn's just beautiful, okay? You know, we can't, we're always really interested in seeing Saturn, how Saturn looks. And with the Opal program in particular, they're studying the atmosphere and how it changes. However, this image is special, not because of the atmosphere, which is still cool, okay? It's still cool, but it's also because in this image, ring spokes appeared. You see that those little blotches there in the rings? Those are called ring spokes, okay? And this is a new thing recently, okay? We have seen them originally starting with the Voyager 2, and Voyager 2 went by Saturn in August of 1981. And again, you can see these smudges in the rings, which is the first time we ever saw these ring spokes. They were also seen by the Cassini mission. Remember the Cassini mission that was at Saturn for like a decade? The Cassini mission saw them starting in September 2005. And here you can see, instead of being the dark smudges that Hubble and Voyager saw in those previous two images, here you have some bright ring spokes in Saturn's rings in September 2005. So why is the seasons on Saturn important? Because astronomers seem to have noticed that the ring spokes might have something to do with when Saturn is at equinox. Okay, so equinox is the transfer from winter to spring. They have the spring equinox, and then it's also the transfer from summer to fall, which is the fall equinox, right? So at the equinoxes, they find that this spoke activity is more prevalent, or is only prevalent around the equinoxes. And so if you notice here in August 1995, you can see the rings edge on. That would be around the equinox, when Saturn's rings are flat on to the sun. Okay, that would be the transfer between northern winter and spring, or between summer and fall. I'm not exactly sure. I guess this one is going into southern summer, going in the sequence that we see here. Well, what we know about Saturn now is the next equinox is coming up in 2 years, in May 2025. And so the astronomers are excited to see these spokes with Hubble, and have the clarity to be able to look at them and to study them over the course as we progress into the equinox and after the equinox, to see how these spokes are, because we don't actually know why the spokes appear. There is a dominant idea, hypothesis, that has something to do with Saturn's magnetic fields, and so that I'm not exactly sure why that would be activated at equinox, but that's what they tell me, that it has something to do with the orientation of Saturn's magnetic field as we get to equinox. And so they're going to be looking at Saturn carefully over the next several years to see if they can test this hypothesis and what they can come up with as to what are the reasons that these spokes appear and that they seem to be seasonal in their appearance. Our second story is detailed galactic structure with fangs. Yes, gonna sink our teeth into this story here. Let's start with a ground-based image, okay? This is a ground-based image of the Whirlpool Galaxy, also known as Messier 51. Honestly, it's my favorite galaxy, okay? It's just a gorgeous grand design spiral galaxy. But what's really cool is when you look at the view in visible light, and you contrast it to the view in infrared from the Spitzer Space Telescope. All right, so this is the visible light view, and this is the infrared view. And it's really kind of cool because you see all this glowing gas in the infrared. Well, if you go back to the visible light, that's all the dark gas. Those dark dust lanes that are opaque in visible light become emissive in infrared light. And you get to see all that internal structure of the gas within the spiral galaxy. The thing is, however, Spitzer isn't that high resolution, especially if I take that Spitzer image and then I compare it to the Hubble image. And it's like, whoa, there's just so much more resolution in the Hubble image, okay? Oh, I left KPNO here. That's not Kitt Peak National Observatory. This is a Hubble image, okay? Oops, my bad. But here's the Spitzer image, and there's the Hubble image, and the Hubble is such higher resolution. Wouldn't it be really cool if we had an infrared telescope with the same resolution as Hubble to see those structures in this kind of detail? And of course, you know where I'm going with this because we have the James Webb Space Telescope up there now. But first, I need to tell you a little bit about the FANGS survey, okay? So the FANGS survey started out at the Atacama Large Millimeter Array, ALMA. All right, it started out as a survey at ALMA to look at nearby spiral galaxies. That says physics at high angular resolution in nearby galaxies. Okay, so the NG is nearby NGS is actually nearby galaxies. Got to get that S in there. And ALMA is good as a radio survey of looking at the carbon monoxide molecule, which traces the cold star-forming gas. Okay, and they looked at the gas disks in 90 nearby spiral galaxies to really start to underlook it. Then they said, let's contrast that with observations from other telescopes. So they did the FANGS MUSE program. All right, and MUSE is a instrument on the Very Large Telescope at Sierra Tololo in Chile, and it's the Multi-Unit Spectroscopic Explorer. It's what we call an integral field unit. Right? And an integral field unit is really cool because it gets images, but it also gets spectra at every pixel. All right, this is a really cool thing. We actually have an integral field unit on J2ST. It won't be used for this, what I'm talking about now, but it's being used for other things. But the MUSE IFS on the VLT was able to do observations of many of these galaxies too. I think it says here 19 star-forming spiral galaxies with MUSE to contrast. And then they said, we want the really high resolution stuff. So where are you going to go? You're going to do FANGS HST. All right. And so Hubble was able to look at 38 of these galaxies in optical light. Okay. And then if you combine all three of those, you take the ALMA and the MUSE and the Hubble and put them together in an image. Here's what NGC 3351 looks like. And so you've got three different wavelengths to look at and get all the various physics of star formation that's going on in these galaxies. But, and you know I was leading here, what we really want is the FANGS J2ST. And last month, in the AppJ letters, the first results from the FANGS J2ST survey came out, okay? And they have a bunch of these galaxies. They're actually doing 19 different galaxies with Webb. And so here I am tonight to show you just the very first results, that's sort of a teaser of what's going on. And we released two images, NGC 1433 and NGC 7496. And look at this. This is what I was telling you about. We're able to see that detailed structure of the gas and dust using these mid-infrared observations from the Webb Space Telescope and really see the detail in that fine resolution that I've been dreaming about for like a decade or two. All right, this is really great. So we're able to see the structure going on in here. And what's really cool in 7496 is that we're also seeing, you see that red light coming from the center? That's an active galactic nucleus here. All right, and you're going to hear about a few things about active galaxies here. And it turns out that J2ST's mid-infrared observations actually do see the emission from the material around active galactic nuclei here. So this is just the beginning of what we're going to get from Fang's web. And we're going to have to do all the correlations, the cross correlations against the visible light from Hubble, the spectroscopic observations from Muse, and the radio observations from ALMA. And being able to look in multiple wavelengths gives us more information to diagnose the physics that's going on in the star formation in these nearby spiral galaxies. So our speaker tonight is Travis Fischer, and he will be talking to us about active galaxies. Travis is here at the Space Telescope Science Institute as an ESA Aura astronomer, and he's been here since 2020, although he tells me he has not spent much time in his office because he got here just before the pandemic started. He got his undergraduate degree at the University of Wisconsin. It wasn't the University of Wisconsin, the main campus. I forget the name of the sub-campus that he was at. And then he did his graduate work at Georgia State. And then he was able to move to the Washington, D.C., Baltimore area and work at three places: the U.S. Naval Observatory, where he was a researcher, at the Goddard Space Flight Center, where he was a JUST postdoctoral fellow, and then finally he settled here at the Space Telescope Science Institute. It's been nice that many astronomers actually move all around the globe during that period after graduate school, but he's been able to have a relatively calm moving possibility, which has allowed him to develop his family. He's got 2 kids. He says he likes hiking and the outdoors. So hopefully we won't lose him to Colorado, like where several of our friends, several of my friends who are astronomers love it because they really enjoy the hiking outdoors. But we got Travis here and we're keeping him. So ladies and gentlemen, Dr. Travis Fischer.
Frank, thank you so much. Thank you very much for having me tonight. Let's get to it. I'm here tonight to talk to everybody about active galaxies. And this is just like a broad talk to kind of understand why we consider them the monsters of the universe, the monsters of the deep space, right? And so before we get there, we're going to have to kind of slow it down and just start with the building blocks about like what is like a galaxy, first of all. So, we can't just jump right into AGN. So what is a galaxy by itself, first of all? And so a galaxy is going to be just a cluster of billions of stars, and some gas and some dust that's all held together by gravity. So these are Hubble images of a bunch of nearby galaxies as part of this LEGUS survey. And we can see it looks like static, but each one of these individual pixels, these little static points, are actually resolved stars in these systems. And we can see that most of the space here is actually empty. But then each one of these little pixels that we're seeing little granulations from, those are individual stars that live in these little communities. So we ourselves live in a galaxy. The solar system lives in a spiral galaxy called the Milky Way. And it doesn't look like any other galaxy that we look at because we're living in it, right? So it looks much more spread out into a simple line. And so here is the image that we usually take from Earth. If you're looking up in the night sky, this is what you would see. And then below that is going to be a cartoon of what we think the Milky Way looks like today. And so you can kind of put yourself in perspective here. If we, how it looks in the image and how it looks from the cartoon is we can just do like a 360 around the cartoon and get an idea that and the entire line that you're seeing in this image of the Milky Way is 100 or 360 degrees around us. And so galaxies at the center of every galaxy, or at almost every galaxy, but we're pretty sure they're in almost all of them, is a supermassive black hole. And so here is the image of the black hole, the supermassive black hole that lives in the center of our galaxy. We've named it Sagittarius A star because we like naming them interesting names. And so this is an image taken from the Event Horizon telescope not too long ago. And so this is what we are going to be focusing on, these supermassive black holes that live at the centers of galaxies. So every galaxy has one of these supermassive black holes, and so the question would be like, what is a black hole itself? What are these objects that we have that are going to be the basis of this talk today? And so to confirm, they are not a wormhole. They are not a portal. They're not a time rift. They're not some sort of gateway to another dimension. It's often you see this sort of like tear in the space-time continuum and have people able to travel through them in science fiction. And so what we want to confirm right now is that these things, these black holes, are objects. All right, they're just like everything else that you would expect to see in the universe. They're just like planets or horses or gallons of milk. These are objects in the universe that exist, and the only real difference between a black hole and everything else that exists in the universe is that black holes are extremely compact. Okay, so let's try to come up with some sort of quantitative or maybe a qualitative comparison of how compact black holes are. So here's a picture of a very massive star. This is an A-type star, much more massive than our sun, about 8 times the mass of the sun that we live around in the solar system. And so when a massive star like this ends its life cycle, it's going to explode and it's going to form a black hole. But the black hole that comes from this explosion is not going to be the size of that star. It's going to be much, much smaller. In fact, if we try to measure what the event horizon is, or the edge of the black hole that we define, it's going to be about 30 miles in diameter. And so for reference, that's maybe the distance to drive across Rhode Island. Okay, so black holes on the stellar mass side are incredibly small. For how much mass is packed inside one of these things. On the other hand, we have the supermassive black hole that is at the center of most of these galaxies, and they are enormous. So this is a 2-scale representation of Sagittarius A star. Sagittarius A star, again, is the black hole at the center of our galaxy, the Milky Way, and the amount of mass that's inside of this black hole is more than 4 million times that of the sun. So that's a huge number, and so it's very surprising then to me that the diameter of this black hole is only going to be about 18 of the sizes of the sun in diameter. So you could stack 18 suns end to end, and that would be the diameter of this supermassive black hole. So this just gives you both of these, the stellar mass black hole and the supermassive black hole. They both are representative of very compact objects that exist in the universe. And to bring it back to the stellar mass black hole, just for comparison size, here is the size of Earth. Right there, I had a flashing pixel down there. That's the size of Earth in comparison to the sun and in comparison to Sagittarius A star. So when we talk about stellar mass black holes and supermassive black holes, they are two completely far ends of the spectrum in the size and scope of these objects. So the question that I most get as an astronomer that focuses on black holes in his career is, are black holes dangerous? Like, are they going to hurt us? Should we be concerned about black holes? And what I like to try to tell people is that, well, I mean, you could swim with sharks, but that'd be very dangerous. Instead, maybe the best idea would be to observe them from a safe distance inside of a cage, and so that you're not even close to that shark. In the same vein, you could look at a volcano while it's erupting. But if you're standing right next to the volcano while it's erupting, you're going to have a bad time. So instead, what you're going to want to do is find a safe distance to observe that volcano and get all the information that you want while not being burned up from the volcano. And then, so if you see where I'm going with this, don't be near a black hole when you're trying to study it. All right, so black holes are dangerous objects if you go too close to them. What we can do, though, is safely sit on our planet Earth and look at all of these black holes that are in space and none of them are going to bother us. They are all at a very safe distance, and viewing them from a remote location means that they're not going to bother us at all. We're going to be okay. So maybe people think that these black holes are dangerous because they think that they're vacuums and they're going to pull everything in. But it's important to know that black holes don't suck. All right. So what we could do as kind of like a thought experiment here is to just take, this is a cartoon of our solar system. As you can see, there's the sun in the center, and there's our 8 planets that are surrounding it. If we remove the sun from our solar system and instead put in a black hole of equal mass, right? So nothing has changed other than the sun has come out and a black hole of equal mass has been in its place, then all of the planets are going to continue orbiting around that black hole as if nothing happened. So they're going to be happily just orbiting around, and since there's no change in mass at the center of the solar system, nothing's going to be affected in how their orbits progress. Although it is true that we are removing all of the heat that's coming from the sun, so we're going to have our own set of problems because there's no sunlight. That's a problem for a different day. So why do black holes then not, like people think that they suck because they don't emit any photons. They're sucking in even light. Light can't escape. How does that work? And so when I try to explain that, I think about a rocket ship and how we try to take a rocket ship and leave the surface of the Earth. All right. So here's a very basic equation where we're just saying if we try to calculate the velocity it requires to escape the surface of something, we essentially just need to know the mass of the object we're trying to escape and also the distance from the center of that object. So to calculate the escape velocity to leave Earth, we would just have the mass of Earth, and we divide that by the radius of Earth. And if we do that calculation, we can see that the velocity that's going to be required to leave Earth is about 11.2 kilometers per second. And I don't know how fast that is. If you asked me to try to figure out how fast 11.2 kilometers per second is, but we can just say that's how fast a rocket goes, because rockets have to be reaching this velocity to be able to escape the gravitational pull of Earth. And to be specific, a rocket's not actually going that velocity. It's going a little bit slower than 11.2 kilometers per second because we're not trying to leave Earth's gravitational pull forever. So if we were trying to maybe send a spaceship to another solar system, another stellar system, some exoplanets or something, then we would want to be going at least 11.2 kilometers per second. But we don't necessarily need to do that to send something up to like the moon, for instance. So that's what escape velocity is for Earth. Let's try to think about what would happen then if we turned Earth into an Earth mass black hole. All right. So the equation stays the same. The mass of Earth stays the same. But the distance that we're using from the center now is going to be approximately the radius of a ping pong ball. That's how large a black hole would be if it was the mass of Earth. And so if we plug in that radius for our calculation, the required velocity to escape the black hole is 1 trillion kilometers per second. Again, another number that makes no sense to me, but you can kind of think of it in the way of comparing it to the speed of light, because this is 3,000 times the speed of light. And so therefore, that's impossible. Like the fastest thing that we know of in the universe is the photon, is the light particle that is traveling the speed of light. Nothing can go faster than that. So if you have a rocket on the surface of that black hole, it's not going to leave because there's nothing that goes that fast. Even though the rockets that the photons live in cannot travel fast enough to escape the gravitational pull of the black hole. And that's why photons are not escaping from black holes. So black holes themselves aren't that scary. However, when you have stuff coming in on a collision course, you're going to have a bad time. So here's an example of a star that's getting too close to a black hole and it's getting pulled apart, shredded, and you have all of this debris forming around the black holes. Parts of it are strewn around, but they're coming back. They're going to be coming in to form a sort of a disk of debris that's surrounding this black hole. And so when we create these debris disks, astronomers call this kind of disk an accretion disk. So accretion is a word for like eating. And so the black hole is eating this matter from the star or from a gas lane or whatever, and it starts spinning around the black hole. And as it's spinning around that black hole, as it's spiraling down the drain, it's heating up. So if you rub your hands together, your hands get warm. And so you can imagine that the dust and the gas and the debris that's spinning around this black hole is rubbing its hands together so fast that it doesn't produce just heat, but also UV rays, X-rays, gamma rays, a flood of radiation. And so when we have this situation go on around a supermassive black hole at the center of a galaxy, we form an event which is called an active galactic nucleus. And for short, we just call that an AGN. And AGN are the monsters then, the giant dumpster fires that we're trying to understand that are wrecking the environments that they live in. So all of that UV and X-ray and gamma ray radiation is flooding out from around this accretion disk, and they're extremely energetic. So what can we do? Like, I tried to come up with a way to, again, quantify the amount of energy that's coming out from an average or even like a low-end supermassive black hole. So I did a calculation for like one of my favorite nearby lower luminosity supermassive black holes, the active galaxies, and I figured, okay, you have an atomic bomb. That makes sense. So let's have, how many atomic bombs do we need? And so it turns out that if you took an atomic bomb for every grain of sand on Earth and you detonated it at the same time, that's not enough. You're not going to create even close to what you need from to create the energy coming from an AGN. Instead, what you need to do is create 160,000 Earths and duplicate them to get all of the sand from those Earths and then turn all of that sand into atomic bombs. And if you detonate all of that at the same time, then you're creating the energy that's coming from a AGN per second. So the amount of energy that's coming out of these things is enormous. It's just crazy big. And so the question then is, if there's all of this energy that's coming from this very small object and the accretion disk surrounding it, like, what does that energy do? And so to come up with a kind of a comparison, like with something that is not necessarily astronomy related, I was watching the show Chernobyl. And so this is a show on HBO. Spoiler alert, Chernobyl explodes. And so there's a scene where there's a lot of folks watching from a great distance, and they're looking at the explosion, and they can see that there's this bright blue beam of light that's shooting up from the where the disaster is happening, and they're saying, wow, it's so beautiful. And so what's happening in this situation is that the radiation that's coming from the reactor meltdown is flooding up into the atmosphere, and it's frying the air molecules that are there. It's stripping electrons off of the air, the atoms that are up there, and it's called ionization. And so I'm pretty sure it's blue then, because the most gas that is in our atmosphere is nitrogen, and so the blue color is coming from the majority of the gas being nitrogen, and that's the color that is going to be most dominant in the ionized gas of our atmosphere. So you can see then, or have an idea, that the only way you can create this glowing gas is if you expose that gas to an enormous source of radiation. So we see then a similar process happening in all of the AGN that we look at. So here's a nearby active galaxy, and we can zoom in to where the nucleus is. And so we can take here is then a picture using the Muse field. So this is what Frank was talking about earlier. This cutout is the Muse field for this specific galaxy. And then we can look at the individual colors of the ionized gas, the fried gas in here, to kind of see the impact that the AGN is having on its host galaxy. So when we turn that filter on, we can see that there's this really beautiful biconical or hourglass shape that's happening here. And this is due to the same process where you're having radiation coming from that central black hole flooding out into the system, and frying that gas. So here's kind of a cartoon that I helped put together at Goddard, where, yeah, so the AGN is shining out into the host disk, and it's kind of acting like a flashlight of doom, where all of the radiation that's coming out from the central engine is frying anything in its path that it runs into. And so that's what you're producing then. You're kind of producing this flashlight effect of where all the gas that's being impacted by the radiation from the central engine. So we can also kind of figure out the impact of that radiation if we look at what we call the kinematics of that gas, using this MUSE IFU data cube where we're having imaging but also spectra. So to just talk about how we analyze that data, we're just going to step into talking about the Doppler effect real quick. So the Doppler effect is where you have a shift of a frequency due to some sort of velocity occurring. So we have an ambulance in this example. The ambulance is making a noise. The ambulance is not moving anywhere. So the sound that is heard by the people in front and behind the ambulance is going to be the same frequency. Alternatively, if you have that ambulance traveling at a specific velocity, the wavelengths in front of the ambulance are going to be squished together and create a higher frequency, whereas the wavelengths behind the ambulance are going to be stretched apart, creating a lower frequency. So the best way to do it is just thinking about like a race car coming towards you, right? So it's a higher pitched sound coming towards you, lower pitched sound going away. And so we can apply that same effect with light. So if we have a light bulb and the light bulb is giving off photons, if that light bulb isn't moving anywhere, the photons that we're seeing on either end are going to be the same wavelength. I'm saying green for this example. But if we have that light bulb having a specific velocity, the wavelengths then get squished together or spread out. And so if it's squished together, we see a bluer wavelength. And if it's stretched out, we see a redder wavelength. And so these are called blue shifts. When the light becomes bluer, it's shifted toward the blue end of the spectrum. And when it's traveling and being spread out, we call that the red shift, or it's being shifted into the redder end of the spectrum. Okay, so we can use that idea of blue shifts and red shifts to equip ourselves to understand the data that we're going to look at right now then. So we go back to our MUSE cube of this active galaxy, and we can look at the velocity of the gas, and we see that most of the gas here is orbiting the center of the galaxy. So what overall this is a big rotating bike wheel, if you will, so that the bottom right-hand field is rotating towards us, and then the upper left-hand corner is, rotating away from us. So the foreground of the galaxy is to the bottom left, and then the background of the galaxy is to the upper right. So this is most of the gas that's happening in the galaxy. This is gas that is maybe attributed to stars that are in the host plane that are rotating around. But then we can also isolate just what the ionized gas is doing, the gas that is being fried by the active galaxy, and we can see what's happening with those kinematics as well. And so we see then here, the AGN is driving the ionized gas out of the galaxy. So instead of our rotation curve here, now what we have is a radial motion, which means it's going from the center, traveling out like along a radius or a spoke and in a wheel. And so you can see that the gas, the fried gas in the upper right-hand corner is being driven toward us. And then the gas in the bottom left is redshifted and being driven away from us. So what you kind of have happening here is the flashlight is running into that plane of the galaxy, and then the gas is running into that and then kind of hitting a dense patch and maybe popping up and splashing upwards. So you guys can maybe think about like that movie with the Little Mermaid, and she's on the rock and she's singing, and the wave comes crashing up behind her because the wave has hit that hard, dense medium and is splashing up to create that displacement out of the plane. And so that's what we're kind of seeing then with this gas being driven out of the plane of the galaxy. And so Besides also noticing what the redshift and blue shift of the galaxy, the gas is, we can actually measure the velocity of this gas. And so when we look at how red shifted or blue shifted that gas is, we can measure that the gas is traveling roughly 300 kilometers per second. And typically it can be greater than that. And so what that really converts to another giant number. It's 670 miles an hour. But more for my human brain, it's like you're traveling from Seattle to Miami along roads, hoping there's no traffic, and you're going to arrive there in a little under 18 seconds. So you can kind of imagine then that this gas is not very pleasant. It's ionized, it's frying the heck out of whatever it's touching the radiation is, and then it's also sweeping everything up and driving it out at bullet train speeds, faster than bullet train, right? It's 18 seconds. It's crazy. So the reason that I say that they're these monsters then is that you see these beautiful pictures that we're always looking at in this ionized gas. And it's very similar to me as looking at hurricanes from space. And you're looking at them and you're saying, wow, nature is glorious, nature is beautiful. But then if you're living in that hurricane, it is the worst. So the same thing would be happening if we're living in an active galaxy. There's tons of radiation that would be pelting our atmosphere and lots of winds that are traveling and blowing everything away, blowing our atmosphere probably away. So we'd be having just the worst time if we're living in this beautiful light echo that we're seeing in these galaxies. So this is why we consider them the monsters of the universe that they are. So the question then is, these things, well, we've confirmed, I believe, that these are monsters. And so how do these AGN affect their galaxies? And we're still trying to figure that out, right? So, I mean, we have a general understanding of what's going on here, but we're not really sure how it's impacting the host galaxy. What kind of effects does this have? And so to try to understand how it's affecting a galaxy, we need to know how stars form in a galaxy. So here's a picture of the Orion Nebula, and we're doing a fly-through of a video that was created to kind of simulate what the Orion Nebula looks like. And as we're traveling through, we can see that all of this gas has formed on itself and compressed down. And when you have enough gas, it's going to ignite through fusion into stars. And you form all of these stars, which eventually blow away their cocoon of gas to reveal themselves. But the point here is that you need all of this gas to form stars in a galaxy. So AGN then kind of affects how stars form, all right? Because the winds are interacting with that star-forming material. So the way that I connect what's happening in a galaxy to my brain is then by trying to compare it to maybe what the physics that you see in a sink at home when you turn the faucet on, right? So you turn the faucet on, sometimes you have this water that's hitting the bottom of the sink, and it pushes it outward until you get to this like ring, this barrier, where this pressure ridge or whatever. And so both of these, both AGN and this faucet situation have the two forms of feedback that I think are important for us to try to understand how galaxies evolve over time. The first one being that AGN can remove gas at small radii to prevent star formation. So you have these winds that are traveling, the radiation is running into the gas and it's pushing it outward and removing any sort of gas that exists at these small radii. And that means you're preventing future stars from forming because you're removing the nurseries. You're not allowing any gas to exist there from which stars can form from. And so what we call this is we call it a negative feedback scenario, where we're removing the potential for star formation. Also, at greater distances, the driving effect is not going to be as powerful in these galaxies. And what we are then seeing potentially is that the gas is being pushed together. And so that is being compressed at greater radii. And then when you're compressing the gas, you're kind of giving the stellar nurseries like a head start or pressing like fast forward, right? Because you're pushing the gas together and making it easier for those stars to form at later epochs. So when you're then promoting star formation, this is called a positive feedback situation. So we're trying to understand both the positive and the negative feedback situations, and we're going to be using James Webb. James Webb is fantastic for revealing the new dimensions, or several new dimensions, of AGN astronomy. And so we can just talk about real quickly what those dimensions are, but Frank did a very nice job of summarizing some of them earlier as well, so I might be repeating him a little bit here. But the first one is that we're seeing a new dimension of space, all right? So nearby galaxies, if they're emitting light in the optical, Hubble got you. Hubble can see that emission from these nearby active galaxies in the optical, and we've learned so much about how active galaxies, regular galaxies, anything in the nearby universe happens to operate in the optical. But as you go to greater distances away from Earth, the universe is always expanding. And again, that Doppler shift comes into play, whereas everything is expanding away from us. That light that once was in the optical is now shifted to the infrared. So we can't observe these more distant galaxies in the same way with Hubble as we're looking at the galaxies in the nearby universe. We can't do a one-to-one comparison. So if we include observations from the James Webb Space Telescope, we're now able to be more sensitive to the infrared light that has been redshifted and is representative of the optical light that is coming from the more nearby galaxies. And now we're able to have that one-to-one comparison to see how does the universe change from these greater distances to the more nearby universe? Well, this one has more emission of this hydrogen line that we see than at the galaxies that are nearer to us, right? So we're able to make this comparison between the optical nearby universe and the infrared universe at greater distances. Additionally, another dimension that James Webb provides us is just wavelength space. So this is also from that FANGS project showing this NGC 7469. And what we're doing is we're blinking between the optical and the Hubble imaging, and then the glowing red here is the dust that's glowing in the infrared. So it's providing, as Frank had mentioned earlier, this additional dimension to these galaxies. So we understand it in the optical light, what's happening with this ionized gas, what's happening with the light coming from the fried gas, but we have very little information about the cold molecular gas that's in these galaxies. So with the infrared light coming from James Webb observations, we're able to have more puzzle pieces to put together to tell that story, to be what I guess you could be like a gumshoe or a detective, where you're gathering all these different clues for the same target using different wavelengths, different wavebands, to come up with a cohesive story of what's happening in each of these nearby galaxies. And then the other dimension that Hubble is bringing us, again, as Frank had mentioned, is resolution. So this is there was a previous Spitzer image here, and then we were able to transition to what James Webb brings us now. So James Webb has a much larger mirror, and so we're going to be able to pick up much finer resolution imaging. And additionally, since it is a larger mirror, we're also collecting more photons per observation hour. So we're going to be able to collect more photons and then have a sharper image of where those photons are coming from, thanks to the James Webb observations. So, if you think about that, what does that mean for me? Like, what do I do with James Webb, with AGN? Like, how am I involved in all of this? Well, so what I'm trying to understand then is how the ionized gas that we were looking at in all of these previous observations, right now, I'm really interested in how they're aligned with the radio emission. So radio is still light. It's at the far end of the electromagnetic spectrum. And we're seeing that the radio structure, which is the blue contour maps in this slide, is related to the fried ionized gas that I was talking about earlier, which is the green in this slide. And so often in AGN, we see them aligned, but There are also these really beautiful radio loud galaxies that have these magnificent jets. So you can see that the galaxy is kind of perpendicular to this very beam-like structure here. And so folks are seeing these radio jets, and then they see the radio structures in these other AGN, these less magnificent ones, and they say, are these processes related? And so what I am not so sure of is whether they are related. I think that they might be due to different processes. So when we're looking at active galaxies that don't have those magnificent plumes of radio, we often see that the radio structure is aligned with the ionized gas. And here's a train of many different papers that compare the maps are often the ionized gas and the contours are the radio data. And we always see the radio data that is intertwined with the ionized gas here. And so what that's suggesting to me is that the radio structure is always in the plane of the host galaxy, because that's where the ionized gas is coming from. It's molecular gas lanes that are being lit up by that flashlight of doom. And so if the radio structure is along where that flashlight of doom structure is, that means that the radio always has to be in the plane of the galaxy, which would be weird if it was just a jet, a plume that could be at any individual inclination. So what I'm testing right now is that the radio structure that we're seeing might actually be due to the winds that are launched from that active galaxy in the center, slamming into dense medium that it can no longer drive out away from the center of the galaxy. And when you have these high velocity winds that we talked about earlier, traveling hundreds to thousands of kilometers per second, they slam into this dense molecular gas that it can't drive anymore, and it creates this shock that's very similar to what you'd see in like a supernova remnant. And so what you're seeing then are just galaxy scale supernova remnants that are producing this radio structure that looks like those plumes that we see in some of these other AGN. So that kind of brings us back to the beginning then. So I had this picture of a galaxy at the beginning of the talk, and what's going on with that is that we are planning to observe this target with James Webb later this month. I'm super excited. So this is a very nearby galaxy that has these radio plumes going on here, and I want to test whether the radio structure, this blue S-shaped structure that you're seeing here, lies along where that glowing dust is in the imaging that we showed earlier. So we're going to compare the blue structure here with the emission that we're seeing from the James Webb infrared cameras to show that, again, the radio structure is in the plane of the host disk, because what's probably happening is that the winds are launching outward, shocking the material in the host galaxy, and producing this, what looks like a plume or a jet, but it's actually just a giant galaxy-sized supernova-esque remnant. So, to wrap up, AGN are dangerous. Are we in danger? And I would just like to dissuade you from being nervous, because we've seen that the Milky Way had an active period about 2.6 million years ago, and that the evidence of this active period is highlighted by these high energy bubbles that are driven perpendicular from the host galaxy. That is that line that we looked at earlier. So here's kind of an animation of what's happening here, right? So here again, the radiation field that's coming from the active galactic nucleus in the center is pointed out of the plane of the galaxy, and we're probably not going to have to deal with any of the massive amounts of radiation that would be pouring out of it as it's pointed out of the plane. So we're probably relatively safe. So with that, I thank you so much for your time, and I'd love to answer any questions that you have. Thanks again.
All right. Thank you very much, Travis. That was probably the most active talk that we've ever seen. I guess on active galaxies is kind of, but you use more transitions and animations and such than anybody else do. So big applause for that. That was extremely well prepared. So I get to ask the first question. And my first question for you is, let's get into this active galaxies as to how long they remain active. Okay, and so like it's just sort of two questions in one. Is that you say that the Milky Way is not active now, but it used to be active. Okay, so at any one time, what percentage of galaxies are active? That's sort of related to how long does a galaxy remain active once it becomes active? What percentage of its lifetime is it an active galaxy?
Right. So galaxies are active, and it's not because they don't just turn on necessarily. There has to be a reason that the material is funneling into that supermassive black hole, like that star that was traveling toward the black hole. It wasn't just on a happy path. It was probably flung there from a binary system or some reason to be flung out of its orbit toward that black hole. So galaxies often undergo mergers, or there's maybe some sort of stream of gas that's coming from a neighboring galaxy that falls in to activate the supermassive black hole at the center of the galaxy. And so we see that often it's only a few percent of all of the millions of galaxies that we know of are active at any given time. And we're not really sure how long an active period in an AGN lasts. I don't know if I've ever seen one ever turn on or turn off necessarily, but they should last. We think that they last like a couple 100,000 years at a time. But yes, I've never seen one turn on or off, I don't think.
So nobody just sort of flips a switch and says, "Okay, you're now active,"
right.
and then, all right,
That's
hey,
right.
hey, I need some quiet over here. Stop being active.
Yeah, we're done. Yeah.
Wish you could do that with your kids sometimes, right? So Grant Justice has been monitoring the chat. We've had an excellent chat here, I think. Grant is going to join us and pull some questions from that chat for you. What have you got for us tonight, Grant?
First, before I begin the questions, I have to say Flashlight of Doom is the best descriptor I've ever heard in a public lecture series.
That's right.
So
it's not a good time.
A plus. A
Yeah.
plus. All right. So first question starting off. Do supermassive black holes behave differently from quote unquote regular black holes because they were formed through a different process?
Well, we don't know how supermassive black holes form. So that would be a good question or a good answer to figure out, first of all. But no, any black hole essentially has a mass, and a spin, how much it's spinning. And I think that no matter the mass of that black hole, those are the two parameters that we know about the black hole. So, I mean, there's been a lot of work to try to understand. So you see, like the stellar mass black holes are often eating material from a binary star system. So it's a black hole and a star companion. And so it's eating the material off of that stellar companion and creating an accretion disk, and there's material flying off of it. And we want to be able to relate that to what we see in AGN, but it just hasn't clicked so far. So it's just the environment is just a little different between the two that we can't really compare the science that's going on between them. But they are relatively the same object.
Right. And if I remember my graduate school work, there were 3 parameters a black hole could have: a mass, spin, and charge. But they're so large that they generally would never ever get a positive or negative electric charge. It would all balance out. That's what I remember.
Gotcha. So at the beginning, you mentioned that black holes are very much not as you would expect from the Hollywood depiction, per se. But what does happen to time near or in, per se, a black hole? I mean, you knew it was coming. You knew.
Come on, Travis. You know that questions like this are out there.
Yeah. I mean, I don't know.
That's a fair answer, though. We're all
learn. But I mean, it's just because of my inexperience with it. Because ideally, like I go to these conferences looking at active galactic nuclei, and there's a whole spectrum of people that start from the very center where there's the black hole and the accretion disk, and then there's like around that is a big dusty torus, and then Past that is like maybe like the high energy people, and then I'm way out here that's looking at like the winds interacting with the host galaxy and what that's doing. And so even though we're all the same like astronomers, I don't know what's going on. Like I don't have the answers for what's going on down there because I'm not ever talking about it enough. So I don't have the brilliant answer for that.
Sure, it's a highly specialized field of study. There are many different facets, so all right.
Yeah.
I'm gonna go home and cry that I'm not the astronomer I should be.
There are folks who specialize in trying to tell the public what a black hole is like. The one thing I remember from all these discussions of supermassive black holes is that the Schwarzschild radius is so large, it's solar system size, such that your spaceship passing through passing in through the event horizon wouldn't really be as stretched out as it would be working with a stellar mass black hole. The field is much more spread. I don't know. It's still intense, but it's the tidal forces aren't as strong, right?
Yeah.
That's all I remember.
Okay.
Gotcha. I would say to the user who asked, I think your name was U2, just go ahead and check some of our other public lectures. We've had quite a few on this, and I'm
from the more
positive we'll
knowledgeable
have
astronomers. Go find them. And
no, someone who specializes in that particular section of black hole study. Don't apologize for having a specialty. It's a good thing. All right. Have we observed any AGNs that are ending an active period and becoming inactive?
We sort of covered that.
Oh, we kind of covered that a little bit more in the beginning.
Yes, we've never seen one turn off. But we do see like these light echoes, right? So the radiation is traveling at the speed of light. It can't go any faster than that. So you can see some galaxies have these radiation, these ionization. The flashlight is still on at great distances, but the AGN has turned off since then. And so at smaller distances, the flashlight is off, right? So you see, we call them foreworks. So the radiation has run out, it's running through the host galaxy or whatever it's running into, but the AGN is now off. So there's it's just this cloud of ionized gas by itself. That's because the AGN has turned off.
Okay, so that begs the question: is how do we know that we see the bubbles in the Milky Way? How do we know it was 2.6 million years ago? For those bubbles were created.
I'm not sure. I was touching base with some folks about that, but I think it might just be the energetics and the required velocity that things are traveling to puff up that bubble at the velocities that they're traveling now. It would require you to walk back 2.6 million years ago to see that.
Valid. Okay. So you had mentioned radio structures at the very end of your talk. What frequencies do you observe those at, and what about radio emissions from galactic jets such as NGC 2663?
I'd have to go on Google to know what 2663.
Yeah, what is that one specifically? Hold on, NGC.
But I mean, this relates to things like Hercules A, or you mentioned Centaurus.
It's an elliptical galaxy. Okay, got it. So, an elliptical galaxy, there are these structures, and I showed them in that image of Centaurus A. You have these radio jets, and the radio jets are prominent in what are called radio loud AGN. So while AGN only are a few percentage of all of the galaxies in the universe, radio loud AGN are only a few percentage of all of the AGN in the universe. And so you have these environments where you're producing these very long plumes, these jets, these radio jets of relativistic plasma. This stuff is traveling almost the speed of light, and you can measure like traveling at these relativistic speeds when we observe them over time. And so the point that I was trying to make then is that in a lot of these radio quiet AGN, which is the majority of AGN that we study, we also see radio structures. And so folks see these elongated radio structures and they say, boom, that is also a jet, because I know what a jet looks like, and it looks like that. So, but what I'm trying to show or confirm or find evidence to deny, we're just testing it out, is to find out if that radio structure is not a jet. It's actually a shock process similar to what you're seeing in the supernova remnants, okay? So you have the winds that are running out from the center of the galaxy. They're running into host disk material, shocking it, and producing that radio structure as kind of like a splash along the edge of that dense molecular gas lane. So a general hypothesis or test would be, if these aren't due to winds running into material, there should be these jets in these radio quiet AGN that are traveling at angles that are not aligned with the host disk. But every single galaxy that I've looked at, I showed in that train of images, always shows that the radio structure is aligned with the ionized fried gas, which means that it's always in the plane of the galaxy. So NGC 2663 is an elliptical galaxy. I'm presuming it's radio loud, and it doesn't have any sort of gas to be running into, and it probably has a pencil beam radio jet. And that is not the same, then, as what we're seeing in a majority of these AGN. And so right. Why is that important? Because then we can start measuring the amount, the distance at which positive feedback, where you're compressing that gas, the maximum amount of, the maximum radius at which positive feedback exists. And so this is just helping us understand the overall picture of AGN feedback then, by knowing that it's not a jet, invoking a jet, but it actually is a byproduct of the winds interacting with the host galaxy.
Right. And we should make sure that our audience understands that elliptical galaxies generally have very little gas and dust, right, in them, so that it can't run into stuff, all right, that doesn't have it. So versus the spiral galaxies, which would be more what you're studying.
That's right. So yes, most of these radio loud galaxies are the elliptical galaxies, which are red and dead. There's not a lot of gas. What's behind me here is a spiral galaxy, so you got lots of blue stars happening here, a lot of young star formation, a lot of gas to form stars. Ellipticals have little to no gas in them, and so all the stars are just the smoldering embers of the low mass stars that still exist there.
All right. Grant, what else have we got from the chat here tonight? Keep seeing
I've seen
new
a
messages
variation
up here.
Yeah, I have. I've seen a couple of variations of the same question, which is, what causes the jets to shoot in their particular directions rather than just anywhere and everywhere?
Great. Yeah. So what we think is happening when you're creating a radio jet is that, so we have seen the accretion disk. Let's actually kind of go back. Can I play my slides a little bit again?
Yeah,
absolutely.
No problem. Start your screen share again.
Yeah. So here's this animation that's showing the material is being stripped from this star and is forming the accretion disk around the black hole in this animation. And so our models predict that what you can see here, perpendicular to that accretion disk, is the radio jet in this cartoon. So the jet that is being emitted by this black hole in this system is going to be perpendicular to that accretion disk. So if we say that the radio jet is related to the orientation of the black hole and the accretion disk, if that means there is no relationship between the orientation of the supermassive black hole and its accretion disk with the greater galaxy. All right. So if the galaxy is in the plane of this plane, and the accretion disk doesn't also have to be in that plane. It can be pointed like this, and then the winds are traveling in this direction. So it can be at any random orientation versus that of the host that it lives in. However, what we're finding then is that the radio jet is always perpendicular, I guess it's always running into that plane of the host disk material. So if it was just a jet, it should be at some random orientation shooting out at any sort of direction. but it's always pointed so that the radio structure is along that plane of that host galaxy, of the material that we're looking at in that galaxy.
So you're saying that the radio emission basically comes from the interaction of where the jet hits the material that's in the disk of a galaxy.
So I'm saying
you get that orientation.
Yeah, so if it was a jet, it would be a relativistic plasma that's traveling perpendicular to that accretion disk going off somewhere. But what we're seeing then is that the radiation from the AGN is probably running outward into that host plane material and smacking into it, compressing it, shocking it, and then the radio structure is formed right there. So you create a bunch of cosmic rays or a bunch of free particles from the shock happening, and then the shock travels along magnetic field lines in the gas, the cool gas that's there, and that produces what's called synchrotron radiation. So that's a radio emission. That is when particles travel along magnetic field lines and emit this radio structure. So that's the radio that you're seeing then. And since you're forming that splash along maybe like a spiral arm or some sort of dust lane, that splash looks like it's called collimated. It looks like it's collimated like the beam of a jet. So that's why people say, oh, that looks like the jet that I'm used to looking at. But what it is, it's a red herring in that sense, is that it's not actually being collimated.
Right. So, I mean, that's an interesting point of view, is that the interesting point to make, that the radio emission happens where the energy gets deposited into the material that it runs into. Right?
That's right.
I remember the same sort of thing is true for some radio loud stuff in terms of you getting the synchrotron radiation wherever it slows down, which is, in those cases, well outside the visible extent of the galaxy, which is
right. Yeah, really so you can't trace like a molecular gas lane of the host galaxy alongside those radio jets. Those radio jets are doing their own thing, and you can't trace parts of the galaxy to be intertwined with the radio structure in those cases. But in these radio quiet AGN, you often see that the radio emission is, I keep saying, intertwined with the ionized gas, which means it's always lodged into the host plane, the host material of that galaxy.
Cool. All right. Any more questions we've got there, Grant?
Yes. AC is keeping me honest. The first part of our previous question, what frequencies do you observe?
Sorry.
Good.
Yep. So these are typically, you're looking at this continuum emission. And so the synchrotron is formed in a continuum emission that we observe with the VLA, the Very Large Array, the Jansky Very Large Array in New Mexico. And we also can use the Very Large or Very Long Baseline Array, the VLBA, to look at that same continuum at even smaller scales. And that's an array of radio dishes from Hawaii to Florida. And so it's an enormous interferometer. But it's typically around like 8 gigahertz, if we want a number there. So it's in the 1s to 10s of gigahertz.
All right, sounds cool.
They're already asking when your second talk is going to be after the next round of observations. Are some galactic central areas more dense? They use the word clumpy, causing more fluctuations or more activity with time?
Sure. Yeah, right? I mean, so...
It would make sense logically, but...
The material is generally got to be fed in to the black hole somehow. So it's usually some sort of gas lane that's falling into the black hole for these active galactic nuclei. But I mean, that could be formed from a merger, or I mean, maybe you have a ring of star formation, like a starburst ring that's going on, and that's creating a bunch of winds off of the stars, and those winds are falling into the black hole in the center. So typically, I mean, I don't know how the environments differ necessarily from quiescent galaxies, galaxies without an active galaxy, or an active nucleus in the center. So Frank showed the Whirlpool galaxy early on, this beautiful grand design structure with the dust lanes and stuff. I don't know why those dust lanes aren't falling into the supermassive black hole at the center. So, I mean, if you told me that that one was not an AGN and that another one was an AGN, I wouldn't be able to necessarily tell just by looking at them. So, yeah, I'm not really sure then.
But, the other thing is that the feeding timescale for a supermassive black hole is well beyond a human timescale. So, I mean, I guess there is sort of a record of the feeding in the jet, right? As you said, it takes time for that jet to propagate, or the energy to propagate out.
Yeah, the radiation
right?
coming from that central engine.
Out. And so if it had an especially active time of feeding, then there would be an especially intense region somewhere out.
Yeah.
And
there's been some work on that.
Could you deconvolve the energy history of the black hole from stuff?
So it's really hard for me. So okay, if you had just a very even plane of gas that the flashlight was shining onto, and it was all just like the same medium, like same density and stuff. If the flux intensity changed over time, then you'd know this was an more active period where it was flaring, and then it was less active here. But the surface that you're shining on is just so irregular too that it's really hard for me to try to pull out where it was brighter and where it was fainter. But you're right. Yeah. I mean, if you were able to do that, you could see what the activity of the AGN was like over time. It was eating a bunch of stuff at this period, and this gas is a lot brighter than it should be than the gas next to it. Right.
The variations in the intensity of the flashlight of doom.
That's right. Oh, that's that's definitely a Indiana Jones.
It is.
Sorry.
Is that our PhD thesis project, right?
Yeah.
I was thinking Mega Maid. All right.
Okay.
AC who asked our previous. I got two. Two?
Okay, two more. Okay, yep.
Two more. Okay. AC, the asker of our previous questions, as an amateur radio astronomer, he observes the 21 centimeter natural hydrogen emission from our galaxy at about 1420 megahertz.
Right. So that is emission from a gas line. So that traces where the where the hydrogen gas is. And so, as we were talking about with the difference between Hubble and with James Webb, looking at these different colors or these different frequencies are going to give us different dimensions of the structure that's going on there. So that 21 centimeter line is super helpful for tracing gas lanes. And I know that I remember writing a paper that we were able to say, oh, this AGN is active because it's accreting material from its neighbor over there, because we can trace the 21 centimeter emission from that galaxy to our galaxy. And so but that's a different, yes, that while it is a radio emission line, it is telling us a different bit of information that we use also to create the story of understanding what's happening in each of these galaxies.
Yeah, it's really important to understand that these different emission lines come from different physical processes. Simple to understand that, gas at 3,000 degrees emits one emission line, gas at 10,000 degrees emits a different emission line. Same thing happens in the radio in terms of the different radio emissions.
And it doesn't have to be different wavebands either. In the infrared with James Webb, you're looking at warm molecular gas, which is a couple hundred degrees Kelvin, and there's emission lines right next to it that is quintuply ionized nitrogen or neon or something, and it's right there next to it. So if you look at those two different lines, they're going to tell you completely different stories, even though they're almost the exact same wavelength.
Right. And as we emphasized, it's the underlying physics that you're getting a handle on from the various things that you were observing. Okay, you said you had one more, Grant?
Yes. We always get one snuck in really good question, and I'm going to end on this one.
Okay.
How have you found ways to keep astronomy real and grounded for you? I found it can become academic over time and kind of lose its magic.
So I always consider myself as I've alluded to a couple of times tonight, like I'm a detective, I'm a gumshoe, and like I'm using all of this data from different wave bands to tell these stories. And I'm not a survey person. I don't look at hundreds or tens of galaxies usually at a time. I look at one really hard, and with like in the optical and the UV and the infrared, and I use that to glean some new facet of how AGN work and how that really works with all of the rest of the AGN that we look at. Right now, I mean, this radio thing is just the worst, because I'm very convinced that this is what's happening in these radio quiet AGN. And so I'm spending a bunch of time trying to convince other people that this is the case. But I feel right now that I'm in the minority. So that is my quest right now, is to have folks acknowledge that this is potentially what's going on and how useful it would be if that is the case. Because then we can see, like if we just do a radio survey of this continuum emission, we can see, we can take a census of how many AGN are shocking or compressing the gas of their host galaxies for all the nearby galaxies. So then when people model how outflows work in AGN, they can say, well, we should have the outflows run into the host plane approximately 40% of the time, because that Fischer guy found that the extended radio structure happens about 40% of the time in these galaxies. That would suggest that that's where positive feedback is happening, and we'll have to incorporate that into our models. So that's what's keeping me going right now. And so that's going to keep happening until the money runs out or something else is more attractive to me. But that's what I'm doing.
That's a good way to think of it, though.
But that's the fun thing about science, is there's always another problem to solve. If you get bored with this problem, which, this is quite a fun problem, I must say, but there's always yet other problems to go, so you can just say, okay, let's cut. That's the end of this season. Let's move on to the next season of, Galactic Detective.
That's right.
I like the specific work, the word that you used is quest. Because it just makes me think that it's not like another project. It's not another thing you're discovering. It's a side quest.
Yeah. It's like, here's a data set. We're going to figure out why this data set is important and what it's illuminating for us. And then that's just part of the bigger picture. But, and then there's always another quest on the horizon that you're finishing this one and you're like, what am I going to do after this? And then you're like, that one, I have to go work on that idea next.
Yeah.
That's
all right. Well, we wish you the best of luck in your continuing series of quests. And when you get the answers, come on back and let us know. Next month, April 4th, exploring rocky worlds on the precipice of a new frontier. Catherine Bennett from the Space Telescope Science Institute. We will see you then. Thank you all for listening, and have a great day.
Bye, everybody.